Pluto's revenge. Why the smallest planet still rules our hearts. Part 1. Pluto's discovery and early mystery. The year 1930 marked a significant moment in astronomical history with the discovery of Pluto. For decades, astronomers had suspected the existence of a ninth planet beyond Neptune, often referred to as Planet X. This search was driven by subtle gravitational perturbations observed in the orbits of Uranus and Neptune, suggesting an unseen massive body tugging at them. Percival Lowell, a prominent astronomer, initiated systematic searches, though he passed away before success. His legacy, however, inspired others to continue the quest, eventually leading to a young astronomer's groundbreaking observation. Clyde Tombaugh, working at the Lowell Observatory in Flagstaff, Arizona, was tasked with the laborious and meticulous job of comparing photographic plates of the night sky. He would examine countless stars, looking for any object that shifted its position against the background stellar tapestry over several nights. It was an incredibly painstaking process, requiring immense patience and keen observational skills. His dedication eventually paid off, bringing to light a faint, moving dot that would forever change our understanding of the solar system's outer reaches. On February 18, 1930, Tombaugh identified the elusive object. Its slow movement across the photographic plates confirmed it was indeed a body in orbit around the Sun, rather than a closer, faster-moving asteroid or comet. The news spread rapidly through the scientific community, captivating public imagination. A new world had been found, expanding the known boundaries of our cosmic neighborhood. The discovery was a testament to human ingenuity and perseverance in unraveling the universe's secrets, pushing the frontiers of exploration from earthbound observatories. The naming of this newfound celestial body was a matter of considerable discussion and public interest. Eventually, the name Pluto was proposed by an 11-year-old girl named Venetia Burney from Oxford, England. She suggested the name of the Roman god of the underworld, fitting for a distant, cold, and dark world. Her grandfather forwarded the suggestion to Lowell Observatory, and after some deliberation, it was officially adopted. This choice resonated deeply, connecting the scientific discovery with rich mythological traditions, a recurring theme in astronomical nomenclature. Initially, Pluto was believed to be a gas giant, similar in size to Neptune, based on early estimates derived from its apparent brightness. This assumption fueled the narrative of a vast, mysterious planet lurking at the solar system's edge. However, as observation techniques improved and astronomers gathered more data, these initial size estimates began to shrink dramatically. The true nature of Pluto remained shrouded in mystery for decades, a distant, fuzzy point of light even in the most powerful telescopes, sparking endless speculation and scientific inquiry. The early estimates of Pluto's mass and size were wildly inaccurate, largely due to the limitations of observational technology at the time. Without the ability to resolve its disk, astronomers relied on indirect methods such as its brightness to infer its physical characteristics. This led to a perception of Pluto as a much larger object than it actually was. The discrepancy between initial predictions and later, more accurate measurements created a sense of ongoing scientific intrigue, highlighting the challenges of studying incredibly distant and faint celestial bodies. The very notion of a ninth planet so far from the Sun sparked immense scientific curiosity about the formation and evolution of the outer solar system. Its eccentric and inclined orbit, unlike the relatively neat and coplanar paths of the other 8 planets, presented an immediate puzzle. This unusual orbital behavior hinted that Pluto might be fundamentally different from its larger planetary siblings. Scientists began to theorize about its composition and origin, speculating whether it was a captured object or a remnant from the solar system's primordial past. For over 70 years, Pluto held its status as the ninth planet, without significant challenge. It was ingrained in textbooks, planetariums, and popular culture. School children learned the mnemonic device, "My very educated mother just served us 9 pizzas," to remember the order of the planets, with Pluto firmly at the end. This long-standing recognition created a strong emotional attachment to Pluto as a full-fledged member of the planetary family, making its later reclassification all the more controversial and emotionally charged for many. The mystery surrounding Pluto's true nature persisted well into the late 20th century. Its small size, peculiar orbit, and icy composition were gradually revealed through improving astronomical instruments, particularly the Hubble Space Telescope. These observations began to paint a picture of a world far different from the gas giants it was initially thought to be. The stage was set for a reevaluation of planetary definitions, driven by new discoveries that would ultimately challenge Pluto's long-held status and redefine our understanding of the solar system's architecture. The early days of Pluto's discovery were marked by both triumph and a profound sense of the unknown. It represented the thrilling edge of human exploration, a frontier where new worlds could still be found and charted. The scientific community grappled with its unusual characteristics, laying the groundwork for future investigations. This period established Pluto not just as an astronomical object, but as a symbol of discovery and the ever-expanding reach of human knowledge into the cosmic void, fueling generations of budding astronomers. Part 2. The Demotion from Planet to Dwarf. The debate over Pluto's planetary status began to intensify in the late 20th and early 21st centuries, driven by a flurry of new discoveries in the outer solar system. As telescopes became more powerful and observational techniques more refined, astronomers started finding a multitude of icy bodies beyond Neptune, in a region now known as the Kuiper Belt. Many of these objects shared characteristics with Pluto, including similar compositions and orbital dynamics, challenging the uniqueness of the ninth planet. One of the most significant discoveries that directly challenged Pluto's status was Eris, found in 2005. Eris was initially estimated to be even larger than Pluto, possessing more mass. This presented a dilemma. If Eris was not considered a planet, then what made Pluto one? Conversely, if Eris were granted planetary status, it would open the floodgates for dozens, if not hundreds, of similar icy bodies in the Kuiper Belt to also be classified as planets, creating an unwieldy and inconsistent planetary system. This growing predicament forced the international astronomical community to confront the long-standing, yet somewhat informal, definition of a planet. Up until this point, there was no rigorous scientific definition universally agreed upon. The classification of planets had largely evolved through historical convention rather than precise scientific criteria. The discovery of Eris, coupled with numerous other large Kuiper Belt objects, made the need for a clear definition undeniable and urgent for the coherence of planetary science. In August 2006, the International Astronomical Union, or IAU, convened in Prague to address this issue. After much debate and considerable controversy, the IAU passed a resolution that established 3 criteria for a celestial body to be classified as a planet. These criteria stipulated that a planet must orbit the Sun, be massive enough for its own gravity to pull it into a nearly round shape, and have, quote, "edge around its orbit," meaning it has gravitationally dominated its orbital path. Pluto satisfied the first 2 criteria. It orbits the Sun and is spherical due to its own gravity. However, it failed the 3rd criterion. Pluto's orbit is embedded within the crowded Kuiper Belt, sharing its orbital space with many other significant objects. It had not gravitationally cleared its neighborhood, unlike the 8 classical planets that have largely swept up or ejected other bodies from their paths. This failure to meet the third criterion sealed its fate regarding planetary status. As a result of this new definition, Pluto was reclassified as a, quote, dwarf planet. This new category was created specifically to accommodate objects like Pluto, Eris, Ceres, the largest asteroid in the asteroid belt, and others that meet the first 2 planetary criteria, but not the third. While still orbiting the Sun and being largely spherical, dwarf planets represent a distinct class of celestial bodies, different from the major planets, providing a more structured hierarchy for solar system objects. The decision to demote Pluto was met with a passionate and widespread outcry, both within the scientific community and among the general public. Many astronomers felt the new definition was flawed or arbitrarily applied. Public sentiment was strongly against the change, largely due to Pluto's long-standing status in popular culture and the emotional attachment people had developed for the 9th planet. Textbooks had to be rewritten, and a sense of loss permeated discussions about the solar system. The controversy highlighted the often difficult intersection of scientific classification, historical convention, and public perception. For many, Pluto's demotion felt like a diminishment, stripping a beloved celestial body of its dignity. It also brought to light the dynamic nature of scientific understanding, demonstrating that even fundamental classifications can change as new knowledge emerges and as our tools for observing the universe improve. Science is not static, and definitions evolve. Despite the formal reclassification, the debate about Pluto's status continues to this day. Some scientists argue that the clearing the neighborhood criterion is problematic, especially when considering exoplanets or planets in other star systems where the environment might be different. Others maintain that the new definition provides a necessary and logical distinction, helping to better organize our understanding of the solar system's diverse inhabitants. The discussion reflects ongoing efforts to refine our cosmic taxonomy. Ultimately, Pluto's demotion, while controversial, served to refine our understanding of planetary systems and the diverse populations of objects within them. It paved the way for a clearer, more consistent framework for classifying celestial bodies, introducing the concept of dwarf planets and highlighting the importance of the Kuiper Belt. This shift, though initially painful for many, ultimately enriched our scientific vocabulary and offered a more nuanced view of the intricate architecture of our solar system. Part 3. New Horizons and the First Close-Up Images. For decades after its discovery, Pluto remained little more than a fuzzy point of light, its surface features and true nature largely a mystery. All that changed dramatically with the New Horizons mission, a pioneering space probe launched by NASA in 2006. This ambitious mission was specifically designed to be the first spacecraft to visit Pluto and its moons, offering humanity its inaugural close-up view of this distant and enigmatic dwarf planet. The journey was long and arduous, spanning nearly a decade across billions of kilometers. The spacecraft's journey was a marvel of engineering and navigation. Traveling at incredible speeds, New Horizons traversed the entire span of the inner and outer solar system. It flew past Jupiter in 2007, using the gas giant's immense gravity for a slingshot maneuver that significantly accelerated its journey toward the Kuiper Belt. This gravity assist saved years off the travel time, demonstrating ingenious methods of interplanetary travel and highlighting the complexity of celestial mechanics involved in such a deep space mission. After its encounter with Jupiter, New Horizons entered a long cruise phase, essentially a deep sleep, to conserve power and reduce wear on its systems. Ground controllers meticulously monitored its trajectory, making occasional course corrections to ensure it would precisely intercept Pluto. As the spacecraft neared its destination, it was gradually brought back online, its instruments checked and calibrated, ready for the brief but incredibly intense flyby period that would revolutionize our understanding of Pluto. The much-anticipated moment arrived on July 14, 2015. After more than 9 years and a journey of over 4.8 billion kilometers, New Horizons successfully performed its closest approach to Pluto. Traveling at speeds exceeding 14 kilometers per second, the spacecraft executed a rapid flyby, collecting an unprecedented trove of scientific data and high-resolution images. This fleeting encounter marked a monumental achievement in planetary exploration, pushing the boundaries of human endeavor to the very edge of the solar system. The images and data that streamed back to Earth in the following months were nothing short of breathtaking and utterly transformed our perception of Pluto. Instead of a bland, cratered ice ball, which many had anticipated, New Horizons revealed a remarkably complex and geologically active world. The sheer diversity of terrains, from towering mountains to vast plains, indicated a dynamic interior and a surprisingly vibrant geological history, challenging long-held assumptions about small, distant, icy bodies. The first full-frame, high-resolution image of Pluto, famously known as the best picture yet, showed a world far more intricate than anyone had imagined. It unveiled a varied surface with intriguing color variations, hints of geological processes, and a surprisingly youthful appearance in some regions, suggesting recent activity. The clarity and detail of these images provided a sense of intimacy with a world that had, until then, only been an indistinct smudge, bringing Pluto vividly into focus for the first time. The data downlink was a slow and painstaking process, due to the immense distance between New Horizons and Earth. Radio signals, even traveling at the speed of light, took over 4.5 hours to reach us. This meant that the full breadth of the mission's discoveries unfolded gradually over many months, keeping the scientific community and the public in eager anticipation as each new batch of images and measurements arrived, piece by piece, building a comprehensive portrait of Pluto. The mission not only provided stunning visuals, but also a wealth of scientific data about Pluto's composition, atmosphere, and interactions with the solar wind. Spectrometers on board analyzed the surface materials, revealing a rich mix of nitrogen ice, methane ice, and carbon monoxide ice. Thermal sensors measured its surface temperature, while dust counters searched for evidence of impacts, creating a multifaceted picture of this distant world from various scientific perspectives. New Horizons fundamentally reshaped our understanding of the outer solar system. It demonstrated that even small, icy worlds far from the Sun can be geologically active and possess complex features. This discovery forced scientists to reconsider their models of planetary formation and evolution, suggesting that internal heat sources or tidal forces might play a more significant role in shaping these distant bodies than previously thought, opening new avenues for research into dwarf planets. The success of the New Horizons mission stands as a testament to humanity's enduring drive to explore and understand the cosmos. It transformed Pluto from a mysterious theoretical object into a vividly real and intricately detailed world. The images captured by New Horizons ignited a renewed sense of wonder and curiosity about the Kuiper Belt and beyond, inspiring future missions and solidifying Pluto's place, not just as a dwarf planet, but as an icon of scientific exploration and discovery. Part 4: Heart-shaped glacier and icy plains. Among the most iconic and surprising discoveries from the New Horizons flyby was a vast, heart-shaped region on Pluto's surface, informally named Sputnik Planitia. This immense bright basin, stretching approximately 1,000 kilometers across, immediately captured the world's imagination, becoming synonymous with Pluto. Its distinctive shape and pristine appearance suggested a dynamic geological process at play, hinting at a very active and surprising interior for such a small, distant world. Sputnik Planitia is not just a pretty shape, it is a giant impact basin likely formed by a colossal collision early in Pluto's history. However, what makes it truly remarkable is its subsequent infilling with nitrogen ice, forming a vast flowing glacier. This enormous glacier, several kilometers thick, exhibits evidence of convection, where warmer, less dense ice rises and cooler, denser ice sinks. This process creates distinct polygons on the surface, resembling rafts of ice moving slowly over geological timescales. The composition of Sputnik Planitia is predominantly frozen nitrogen, along with smaller amounts of methane and carbon monoxide ice. These volatile ices are soft and easily deformed, allowing them to flow like glaciers on Earth, albeit at incredibly slow speeds. The presence of such a massive, actively convecting ice sheet suggests that Pluto retains significant internal heat, enough to keep its nitrogen ice in a state of slow-motion churn, preventing it from freezing solid to the base. Surrounding Sputnik Planitia are towering mountain ranges, some rising several kilometers above the icy plains. These mountains are thought to be composed primarily of water ice, which at Pluto's frigid temperatures acts like rock on Earth. The sharp, rugged peaks, with almost no visible cratering, indicate that these mountains are geologically young, possibly uplifted by tectonic forces or carved by flowing glaciers, suggesting ongoing geological activity, a startling revelation for such a small world. Adjacent to Sputnik Planitia, and extending across vast areas, are complex icy plains that exhibit a wide range of textures and features. Some regions are smooth and featureless, indicative of recent resurfacing, possibly by cryovolcanic flows or deposits from the atmosphere. Other areas show intricate patterns, including pits, grooves, and ridges, hinting at diverse geological processes like sublimation, where ice turns directly into gas, or interactions with Pluto's thin atmosphere. One particularly intriguing area is the Cthulhu Macula, a large, dark region west of Sputnik Planitia. This area is thought to be covered in tholins, complex organic molecules formed by the interaction of sunlight with methane and nitrogen in Pluto's atmosphere. Tholins are reddish-brown and are responsible for Pluto's overall reddish hue, contrasting sharply with the bright, icy plains and suggesting different geological or atmospheric processes at work across the surface. The discovery of such a diverse and active landscape challenged previous notions that small, distant celestial bodies would be geologically inert. Scientists had largely expected Pluto to be a cold, dead world, heavily cratered and unchanged for billions of years. Instead, New Horizons unveiled a dynamic dwarf planet, with ongoing processes shaping its surface, indicating a complex thermal history and potentially internal liquid water ocean beneath its icy crust, keeping it geologically active. The heart-shaped glacier and the surrounding plains provide crucial insights into Pluto's internal structure and evolution. The evidence of convection within Sputnik Planitia, combined with the presence of youthful mountains, strongly suggests that Pluto possesses enough internal heat to drive geological activity. This internal heat could originate from residual heat from its formation, radioactive decay, or even tidal interactions with its large moon, Charon, collectively shaping its surface. The interaction between Pluto's thin atmosphere and its surface ices is another fascinating aspect revealed by these images. As Pluto moves closer to and further from the Sun in its eccentric orbit, its surface temperature fluctuates, causing nitrogen, methane, and carbon monoxide ices to sublimate into the atmosphere and then refreeze onto the surface. This creates seasonal cycles that can dramatically alter the appearance of its icy plains and contribute to the formation of its hazes. The iconic heart of Pluto, particularly Sputnik Planitia, has become a symbol of the unexpected wonders awaiting discovery in the outer solar system. It transformed a distant theoretical object into a world with tangible, beautiful, and geologically active features, captivating both scientists and the public. These close-up images irrevocably changed our perception of dwarf planets, revealing them as complex and dynamic worlds, full of surprises and challenging our understanding of planetary processes. Part 5. Pluto's thin atmosphere and hazes. Before the arrival of New Horizons, the existence and characteristics of Pluto's atmosphere were largely inferred through occultation events, where Pluto passed in front of distant stars. These observations suggested a very thin, tenuous atmosphere, primarily composed of nitrogen, with trace amounts of methane and carbon monoxide. However, the New Horizons flyby provided the first direct and detailed measurements, confirming its presence and revealing a surprisingly complex and dynamic structure, complete with multiple haze layers. Pluto's atmosphere is incredibly thin, about 100,000 times less dense than Earth's, making it essentially a vacuum by terrestrial standards. Despite its sparsity, it plays a crucial role in shaping Pluto's climate and surface features. The atmospheric pressure at Pluto's surface is so low that if you were to stand there, it would feel similar to the conditions found about 1,000 kilometers above Earth's surface, highlighting the extreme environment of this distant world. One of the most visually stunning discoveries regarding Pluto's atmosphere was the presence of multiple distinct layers of haze. New Horizons captured images of these hazes extending up to 200 kilometers above the surface, appearing as faint bluish layers backlit by the sun. These haze layers are thought to be formed by complex organic molecules called tholins, created when ultraviolet sunlight breaks down methane and nitrogen in the upper atmosphere, which then recombine into larger, solid particles. These tholin particles gradually settle down onto Pluto's surface, contributing to its reddish-brown coloration, particularly evident in regions like the Cthulhu Macula. The hazes also scatter sunlight, producing a faint blue sky effect, similar to Earth's, though far more subtle due to the atmosphere's extreme thinness. The detection of these hazes challenged existing models, as they indicated a colder upper atmosphere than predicted, allowing these particles to form and linger at higher altitudes. The stability and layering of Pluto's hazes suggest that the atmosphere is extremely calm, with very little turbulent mixing. This lack of turbulence allows the individual haze layers to persist for extended periods, creating the distinct banded structure observed by New Horizons. The presence of these stable, high-altitude hazes offers clues about the thermal structure of Pluto's upper atmosphere and the subtle interplay of solar radiation and atmospheric chemistry. Pluto's atmosphere undergoes dramatic changes as it moves through its highly eccentric 248-year orbit around the Sun. When Pluto is closer to the Sun, its surface temperatures rise slightly, causing surface ices, primarily nitrogen, to sublimate and thicken the atmosphere. As it moves further away, the atmosphere begins to freeze out and collapse back onto the surface, creating a dynamic cycle of atmospheric growth and decay, a planetary breathing mechanism on a grand scale. This seasonal breathing of Pluto's atmosphere has profound implications for its surface. As the atmosphere thickens, it can transport volatile ices, depositing them in different regions. This process contributes to the resurfacing of Pluto, helping to explain the youthful appearance of some areas, like Sputnik Planitia. Atmospheric processes can also erode surface features and sculpt ice formations, further demonstrating the active interplay between Pluto's atmosphere and its geology. The detection of atmospheric escape, where gases are lost to space, was another significant finding. New Horizons' SWAP instrument, which measures solar-wind interactions, observed that Pluto's atmosphere is slowly bleeding away into space, creating a long ionized tail much like a comet's. This atmospheric loss is driven by the solar wind stripping away molecules from the uppermost layers, providing insights into the long-term evolution and eventual fate of Pluto's tenuous envelope. The insights gained from studying Pluto's atmosphere have significant implications for understanding other distant icy bodies in the Kuiper Belt. Many of these objects are thought to have similar compositions and might possess similarly dynamic, albeit thin, atmospheres. New Horizons findings provide a crucial baseline for comparative planetology, helping scientists model the atmospheric processes on other dwarf planets and large Kuiper Belt objects, expanding our knowledge of these frigid worlds. In essence, Pluto's thin, hazy atmosphere is far from simple. It is a dynamic system, intimately connected to its surface ices and orbital mechanics, undergoing seasonal changes and slowly escaping into space. The New Horizons mission revealed this complexity, transforming our perception of a seemingly inert world into one with a surprisingly active and evolving atmospheric shell, showcasing another layer of Pluto's unexpected geological and atmospheric vibrancy. Part 6. Charon and the Dance of Binary Worlds. Pluto is not alone. It is accompanied by a surprisingly large moon named Charon, discovered in 1978 by astronomer James Christie. Charon is so large relative to Pluto, about half its diameter, that the two bodies are often considered a binary system, rather than a planet and its moon in the traditional sense. This close relationship and their unique orbital dance make the Pluto-Charon system one of the most intriguing pairs in the solar system, offering a window into tidal forces and binary evolution. What makes the Pluto-Charon system truly unique is that their center of mass, the barycenter, lies in the space between the two bodies, rather than within Pluto itself. This means that both Pluto and Charon orbit this common point, causing them to constantly face each other, a phenomenon known as mutual tidal locking. Just as Earth's moon always shows us the same face, Pluto and Charon are locked in an eternal, gravitational embrace, forever presenting the same side to one another. The New Horizons flyby not only gave us unprecedented views of Pluto, but also provided the first detailed images of Charon. It revealed a surprisingly diverse and geologically active moon, far from a simple, cratered sphere. Charon exhibits a complex surface, featuring vast plains, towering scarps, and even a mysterious reddish polar cap, suggesting its own unique and active geological history, distinct from its larger companion. One of Charon's most striking features is a massive canyon system, informally named Serenity Chasma, which stretches for over 1,800 kilometers across its surface, dwarfing Earth's Grand Canyon. This colossal rift valley suggests that Charon experienced significant internal geological activity, possibly due to the freezing of a subsurface ocean, which caused its crust to expand and crack, creating these enormous tectonic features in its relatively recent past. Charon's north pole is adorned with a prominent reddish cap, informally known as Mordor macula. Scientists believe this coloration is due to tholins, much like those found on Pluto. However, the tholins on Charon are thought to originate from Pluto's escaping atmosphere. Methane from Pluto's atmosphere is captured by Charon's gravity, freezes onto its polar regions, and then undergoes chemical processing by solar radiation, turning into the reddish organic molecules. The surfaces of Pluto and Charon offer a striking contrast. Pluto is a world of volatile ices, active glaciers, and atmospheric hazes, constantly being reshaped. Charon, while showing evidence of past geological activity, appears much older and more tectonically stable, with extensive cratering in some regions. This difference highlights how two closely related bodies can evolve along vastly different geological pathways, influenced by their individual compositions and internal heat sources. The origin of the Pluto-Charon binary system is thought to be the result of a colossal impact early in the solar system's history, similar to the giant impact theory for Earth's moon. A large object is believed to have collided with proto-Pluto, ejecting a significant amount of material that then coalesced to form Charon. This energetic origin would have provided both bodies with substantial initial heat, which could have driven their early geological activity and shaping. The tidal forces between Pluto and Charon have played a profound role in their evolution. Over billions of years, these forces slowed down their rotations and locked them into their current synchronous orbits. This tidal heating could also have been a source of internal energy, particularly for Charon, possibly contributing to the formation of its canyon system and potentially maintaining a subsurface liquid water ocean for a period of its history. The other four smaller moons of Pluto, Styx, Nix, Kerberos, and Hydra are also part of this complex system. These small, irregularly shaped moons orbit the Pluto-Charon barycenter in chaotic, non-Keplerian ways, influenced by the constantly shifting gravitational field of the main binary pair. Their erratic rotations and tumbling motions provide further clues about the dynamics of multi-moon systems formed in the aftermath of a massive collision. The Pluto-Charon system, with its binary dance and diverse geological features, is a testament to the unexpected complexity of the outer solar system. It challenges the notion of simple, inert moons and small worlds, revealing a pair of objects deeply intertwined by gravity and history, each with its own compelling story of formation and evolution. This binary world represents a unique laboratory for studying tidal dynamics, planetary formation, and the diverse outcomes of cosmic collisions. Part 7. The Kuiper Belt Connection. The discovery of the Kuiper Belt in the early 1990s fundamentally reshaped our understanding of the outer solar system and Pluto's place within it. This vast region, extending from beyond Neptune's orbit out to approximately 50 astronomical units from the Sun, is a vast reservoir of icy bodies, remnants from the solar system's formation. It is analogous to the asteroid belt, but far larger and populated by objects primarily composed of ices rather than rock and metal. Pluto is now recognized as one of the largest and most prominent members of the Kuiper Belt. Its reclassification as a dwarf planet stems directly from this connection, as astronomers began to discover numerous other icy objects, many with similar compositions and orbital characteristics to Pluto, residing within this belt. This led to the realization that Pluto was not a solitary planet, but rather a prominent member of a vast population of trans-Neptunian objects. The Kuiper Belt is thought to be the origin of many short-period comets, those with orbital periods of less than 200 years. Gravitational perturbations from the gas giant planets, particularly Neptune, can occasionally kick these icy bodies out of the Kuiper Belt and send them on trajectories towards the inner solar system, where they become visible as comets as they warm up and release gas and dust, creating their characteristic tails. Beyond Pluto, New Horizons continued its journey to explore another Kuiper Belt object, Arrokoth, in 2019. This flyby provided humanity's first close-up view of a primordial KBO, revealing a bilobed, snowman-shaped object that is believed to be a pristine remnant from the very early solar system. Arrokoth's untouched appearance offers invaluable clues about the conditions and processes that led to the formation of planets billions of years ago. The objects in the Kuiper Belt are largely categorized into several types, including classical KBOs that orbit in relatively stable paths, and resonant KBOs that are gravitationally locked in orbital resonances with Neptune. Pluto itself is a resonant KBO, specifically in a 2 to 3 resonance with Neptune, meaning for every 2 orbits Pluto completes, Neptune completes 3. This resonance helps stabilize Pluto's highly eccentric and inclined orbit, preventing close encounters with Neptune. The Kuiper Belt also contains several other dwarf planets, such as Eris, Haumea, and Makemake. These objects, like Pluto, are massive enough to be spherical due to their own gravity, but have not cleared their orbital neighborhoods. Their discovery underscored the need for a revised planetary definition and cemented the idea that the outer solar system is teeming with a diverse population of large icy bodies beyond the traditional planets. Studying the Kuiper Belt and its inhabitants provides crucial insights into the early history of the solar system. These icy relics are essentially time capsules, preserving the original building blocks from which the planets formed. By analyzing their compositions, orbits, and physical characteristics, scientists can reconstruct the conditions of the protoplanetary disk and trace the migration patterns of the giant planets in the early solar system. The NICE model, a prominent theory of solar system evolution, posits that the giant planets, particularly Jupiter and Saturn, underwent a period of significant orbital migration early in the solar system's history. This migration would have gravitationally stirred up the Kuiper Belt, scattering many objects inwards and outwards, helping to explain its current structure, including the presence of objects like Pluto in resonant orbits. The Kuiper Belt represents a vast, largely unexplored frontier. Beyond the objects already discovered, countless smaller KBOs remain unobserved, holding secrets about the solar system's formation. Future missions designed to explore more of these distant icy worlds would provide an even more comprehensive understanding of this critical region and the primordial conditions that gave rise to our planetary home. The Kuiper Belt connection irrevocably links Pluto to a larger population of icy worlds, shifting its identity from an outlier planet to a king among dwarf planets. This understanding has not diminished Pluto's scientific importance, but rather enhanced it, positioning it as a key representative of a vast, ancient, and dynamically active region of our solar system, providing vital clues about our cosmic origins. Part 8. Cultural love for Pluto as a planet. Despite its scientific reclassification, Pluto continues to hold a cherished place in the hearts of many as the 9th planet. For over 76 years, it was an integral part of our solar system narrative, ingrained in textbooks, classroom models, and popular culture. This long-standing recognition fostered a deep emotional attachment, turning Pluto into more than just a celestial body, but a symbol of the distant and mysterious frontier of space exploration. Generations grew up learning the names of the 9 planets, with Pluto proudly holding the last spot. Its unique status as the smallest and most distant planet lent it an underdog charm, appealing to many. The idea of a tiny, icy world so far away, yet still a full-fledged member of the planetary family, resonated with a sense of wonder and cosmic completeness that the demotion seemed to disrupt, leaving a void in many people's perception of the solar system. The popular outcry following Pluto's reclassification in 2006 was significant and widespread. Petitions were signed, protest songs were written, and merchandise proclaiming Pluto is a planet appeared. This emotional response was not just from children, but from adults who felt a personal connection to the Pluto of their youth. It underscored how scientific classifications, when they challenge established cultural narratives, can evoke strong public sentiment, far beyond the academic debate. Pluto's cultural presence extends beyond just being a planet. It inspired characters, such as Mickey Mouse's loyal dog, Pluto, though Disney animators clarified the dog was named after the planet, not the other way around. This connection further cemented Pluto's friendly and familiar image in the public consciousness, making its demotion feel like a personal slight to a beloved member of the cosmic family. The New Horizons mission, with its stunning close-up images, further reignited public interest and affection for Pluto. The revelation of a heart-shaped glacier, towering mountains, and blue hazes transformed a distant fuzzy dot into a vividly real and beautiful world. These images captivated audiences worldwide, reinforcing the idea that Pluto, regardless of its official classification, is an extraordinary and fascinating place worthy of exploration and admiration, cementing its iconic status. For many, Pluto's demotion felt like an injustice, a bureaucratic decision that stripped away its identity. The arguments about clearing its orbit seemed technical and abstract to a public more concerned with the wonder and romance of space exploration. This highlighted a disconnect between scientific precision and the broader, more inclusive cultural understanding of what constitutes a planet, reflecting different ways of valuing celestial bodies. The enduring cultural love for Pluto also speaks to humanity's inherent desire for order and simplicity in understanding the cosmos. A solar system with 9 distinct planets was a clear, memorable model. The introduction of dwarf planets and the nuances of planetary definitions, while scientifically accurate, complicated this simple narrative, leading to some resistance in adopting the new framework, particularly in public discourse. Even within the scientific community, particularly among planetary scientists who study Pluto, there is a strong contingent who argue for its reclassification as a planet. They often emphasize its geological complexity, active processes, and diverse features, asserting that these attributes are more indicative of a planet than simply clearing its orbital path, highlighting that the debate is far from settled, even among experts. Pluto's journey, from its unexpected discovery to its demotion and then its stunning close-up reveal, mirrors a larger human narrative of discovery, challenge, and renewed appreciation. It serves as a reminder that our understanding of the universe is constantly evolving, but also that our emotional connections to cosmic objects are powerful and enduring, shaping how we perceive and relate to the vastness around us. Ultimately, Pluto's cultural love affair as a planet persists because it embodies resilience and the thrill of discovery. It remains a symbol of the distant unknown, now beautifully revealed, and a testament to the enduring human capacity for wonder. Regardless of its official label, Pluto continues to rule our hearts as a beloved, complex, and scientifically significant world at the edge of our solar system. Part 9. Pluto in Mythology and Art. The name Pluto itself is steeped in ancient Roman mythology, derived from the god of the underworld, equivalent to the Greek Hades. This choice, suggested by Venetia Burney, an 11-year-old girl, was remarkably apt for a distant, cold, and dark world at the very edge of the known solar system. The mythological association imbues the dwarf planet with an aura of mystery, power, and a connection to the deepest, most hidden realms, reflecting its physical attributes. In Roman mythology, Pluto was the ruler of the dead, associated with wealth hidden beneath the earth, like precious metals and fertile seeds. This duality of death and hidden riches can be symbolically linked to the scientific journey of Pluto. Initially, a dark, unseen world, then revealing unexpected geological richness and complexity beneath its icy surface through the New Horizons mission, transforming obscurity into discovery. Pluto's mythological connection extends beyond its name, influencing popular culture and artistic interpretations. Its distant and somewhat foreboding nature has made it a common motif in science fiction, where it often serves as a setting for remote outposts, mining colonies, or mysterious ancient ruins. Emphasizing its frontier status, an isolated beauty within the cosmic landscape, a place of extreme challenge and potential. Astronomical art has frequently depicted Pluto, even before the New Horizons flyby, often based on speculation. Early artistic renditions showed a dark, frigid, and heavily cratered world, sometimes with a faint sun in the distance, emphasizing its isolation. These early works, though scientifically informed, were largely products of imagination, filling the void of direct observation and shaping public perception of this enigmatic world. With the advent of the New Horizons images, artistic interpretations of Pluto have become much more detailed and scientifically accurate. Artists now portray Sputnik Planitia's heart, the towering water ice mountains, the reddish Tholin hazes, and the contrasting terrains, bringing a new level of realism and vibrancy to Pluto's artistic representation. These works help visualize the mission's findings and communicate the beauty of this distant world to a wider audience. The stunning imagery from New Horizons has inspired a new wave of artists, photographers, and even musicians. The heart-shaped feature, in particular, has become an iconic symbol, appearing in various forms of media and art, often representing the hidden beauty or the unexpected warmth found in the coldest, most distant places. This emotional resonance reinforces Pluto's unique place in the human imagination, bridging science and sentiment. In contemporary art, Pluto's demotion itself has become a subject. Artists have used the controversy to explore themes of identity, belonging, and the subjective nature of classification. Some works mourn the loss of Pluto's planetary status, while others celebrate its new role as a prominent dwarf planet and a representative of the Kuiper Belt, reflecting the ongoing debate and the diverse emotional responses to the scientific reclassification. Pluto's connection to mythology and art underscores humanity's deep-seated need to imbue the cosmos with meaning and narrative. We don't just observe celestial bodies. We name them, tell stories about them, and create art inspired by them. This process transforms abstract scientific facts into culturally resonant symbols, making the universe more relatable and understandable on a human scale, connecting our terrestrial experiences with the vastness of space. The concept of a dwarf planet, while a scientific classification, also carries metaphorical weight in art and literature, sometimes symbolizing those who are underestimated or overlooked, yet possess profound inner qualities. Pluto, the smallest and most distant of the original planets, now the largest dwarf planet, embodies this narrative of resilience and hidden significance, proving that size does not dictate complexity or wonder. Ultimately, Pluto's presence in mythology and art serves to deepen our connection to this distant world. It provides a cultural lens, through which we interpret scientific discoveries, allowing us to appreciate Pluto not just as a collection of physical properties, but as a character in our ongoing cosmic story. From ancient gods to modern artistic renditions, Pluto continues to inspire awe and imagination, cementing its place in the human narrative. Part 10. Could Pluto regain planetary status? The question of whether Pluto could ever regain its full planetary status is a recurring and passionate debate within both the scientific community and the general public. While the International Astronomical Union's 2006 definition demoted Pluto to a dwarf planet, not all astronomers agree with that decision, and new arguments continue to emerge, suggesting that the criteria for planetary classification might need further refinement or an entirely new approach. One of the primary arguments against the IAU's definition centers on the criterion that a planet must clear the neighborhood around its orbit. Critics argue that this criterion is problematic because no planet, not even Earth, has perfectly cleared its orbit. Earth, for example, shares its orbit with numerous asteroids. The interpretation of clearing is seen by some as vague and difficult to apply consistently across different planetary systems, or even within our own. Furthermore, some scientists argue that the IAU's definition is tailored too specifically to our solar system and may not be suitable for the thousands of exoplanets discovered orbiting other stars. The diverse environments and orbital dynamics in other star systems might make the clearing the neighborhood criterion impractical or irrelevant. A more universal definition, applicable to all planetary systems, is seen as necessary by a growing number of planetary scientists. Many planetary scientists advocate for a geological or geophysical definition of a planet, rather than one based solely on orbital mechanics. This alternative definition would focus on whether a celestial body is massive enough to be spherical due to its own gravity, and if it exhibits signs of active geology, such as volcanic activity, tectonics, or a substantial atmosphere. Under such a definition, Pluto, with its heart-shaped glacier, young mountains, and hazes, would easily qualify as a planet. The New Horizons mission significantly strengthened the case for Pluto's planetary characteristics. The discovery of its complex geology, internal heat, and a dynamic atmosphere challenged the notion of it being a simple, inert ice ball. These findings revealed a world far more active and planet-like than many smaller, conventionally accepted moons of larger planets, further fueling the argument that Pluto should be considered a planet based on its intrinsic properties. The cultural impact of Pluto's demotion also plays a subtle role in the ongoing debate. The widespread public dissatisfaction with the reclassification highlights a desire for a more intuitive and inclusive definition of a planet. While scientific classifications must be rigorous, some argue that they should also resonate with human understanding and appreciation for the diverse worlds within our cosmos, rather than creating confusion or a sense of diminishment. Proponents of the current IAU definition emphasize the need for a clear and manageable classification system. They argue that if Pluto were reinstated, then dozens, if not hundreds, of other large Kuiper Belt objects would also have to be considered planets, leading to an unwieldy and less useful system. The current definition, they contend, maintains a distinction between the 8 major planets and the vast population of smaller, albeit significant, bodies. The debate also touches on the nature of scientific progress itself. As our understanding of the universe expands, especially with the discovery of numerous exoplanets and the detailed exploration of dwarf planets, our classifications must adapt. The reclassification of Pluto, while controversial, was a direct consequence of new discoveries, forcing astronomers to confront ambiguities in long-held assumptions and refine their taxonomy. While a formal reversal of the IAU's 2006 decision seems unlikely in the near future, the ongoing discussion ensures that Pluto remains a focal point in the debate over planetary definitions. The arguments continue to evolve as new data emerges from other distant worlds, and as scientists continually refine their models of planetary formation and evolution, keeping the dialogue around Pluto's status very much alive. Ultimately, whether Pluto officially regains its planetary status may depend on the evolution of scientific consensus and the adoption of a broader, more inclusive definition of a planet. Regardless of the outcome, Pluto's journey has undeniably enriched our understanding of the solar system, challenged our preconceived notions, and sparked a global conversation about what truly makes a world a planet, ensuring its prominent place in both science and popular imagination.